In this video, we're going to see the other applications of a PN junction diode. That is how the PN junction diode is going to act as the base for all other electronic devices. So for example, here we're going to learn about the optoelectronic junction devices. So in these optoelectronic junction devices, we will be using a semiconductor diode. And in this semiconductor diode, what will happen is the carriers will be in the form of photons, that is in the form of light or photoexcitation. So we are going to learn the working of three types of optoelectronic junction devices. So one is going to be photodiodes and LEDs, that is light emitting diodes, and then we'll learn about the working of solar cells and the application of all these optoelectronic junction devices. The first optoelectronic junction device is a photodiode. So we'll see what is a photodiode, what is the use of it, how it has been constructed, and the working of it. So the photodiode is a device which is used for detecting optical signals. So you can detect optical signals with the help of a photodiode. And what we are using in this? So again, we are going to use a PN junction diode, and it is going to be a special purpose PN junction diode. So what is a special purpose PN junction diode here? So here what happens in this photodiode is it will be operated under reverse bias, and it will have a transparent window to allow light to fall on it. So this is how it will be devised. So it is used for detecting optical signals. It will be operating under reverse bias, and there will be a transparent window, so you can see the images over there. So this is the schematic diagram, circuit diagram. So a PN junction we have, and you can see it is connected to reverse bias, a load, and what will happen is light will be allowed to fall upon that transparent window here. And the next one, you have the symbol of a photodiode. So you can see that the arrow marks which have been falling on the diode there. So it says that the diode is absorbing light, and the last image is the real life image of a photodiode. So that's a photo image of a photodiode, what we use in our daily life. Let's see the construction and working of a photodiode. So as I said already, a photodiode, here we'll be using a special purpose PN junction diode, and it will be fabricated or it will be prepared with the PN junction with a transparent window where light will be allowed to fall upon it. So you can see there on that side, the top corner, we have the circuit diagram of a photodiode. So PN junction diode will be connected in reverse bias, and it will be connected to a load and a microammeter. So we'll just see the working of it. So first, when the photons of energy h nu, which is going to be greater than the energy band gap, is allowed to fall upon the photodiode, electron hole pair will be generated. So now you can see in the video there. So already it is in reverse bias. So as it is in reverse bias, the depletion region will widen, it will be more. And when the light falls upon the PN junction diode, it will generate more number of electron hole pair. And as a result of it, the electric field will be generated. And the direction of your electric field will be in such a way that the electrons will reach the P side and N side, and the holes will reach the P side here. And this will give rise to a EMF. And when an external load is connected to the circuit, what happens is the current will start flowing, and this current we call as the photocurrent. So here the photocurrent is directly proportional to the intensity of light. So when the current increases, your intensity of light will also increase. So this is the working of a photodiode. Now we have the VI characteristics of a photodiode. That is, a graph has been plotted for the current and the voltage which has been produced by the photodiode. So as you see the graph, what happens here is, as the photocurrent increases, the intensity of light which is being produced is also increasing here. And as the photocurrent increases, it is also increasing with increase in reverse bias voltage. So as we are increasing the reverse bias current also, the photocurrent which is being produced by the photodiode also increases. But after a certain time, what happens is it becomes saturated. That is, the photocurrent becomes constant. There is no change or increase in the increase or decrease in the photocurrent of the diode. What are the applications of this photodiode? We'll see. So it's been used in safety electronics like fire and smoke detectors, and it is also used in cameras and even in medical applications we use this photodiodes. It's also been used as photosensors also. And in medical purposes, we use for testing the samples or analyzing the samples. So this is the uses of photodiodes. Next, we have an interesting one, that is the light emitting diode. So this light emitting diode, you people have been seen it. You would have used it also. It has different colors also. So what's the use of this light emitting diode? So it will convert electrical energy into light energy. And what happens is, this is also going to be a heavily doped PN junction diode. And what happens here is, this light emitting diode will be operating in reverse bias. And one more thing, if you see in this circuit diagram, you can see the diode, the direction of the arrow mark they've given, it is outwards. So it is understood that the diode is going to emit light. So now the next we'll see how this diode is going to emit light. So already we have seen that photodiode, it is getting light and it is emitting, it's converting into energy. So now what it is going to do is, it is going to get the energy and it is going to let it in the form of light energy. So how it is going to convert it into the light energy, we'll see. We'll see the working of an LED. So this LED it will convert electrical energy to light energy, and it is a heavily doped PN junction diode, and it is going to be operating in forward bias. So here what happens in forward bias is, the electrons will move from N region to P region, and the holes will move from P region to N region. So when the recombination of holes and electrons are taking place near the junction, some amount of energy will be released here. So during this recombination of holes and electrons, some amount of energy is being released, and the energy which is being released here, it will be in the form of photons here. And the energy of the photons here, it is going to be very less than the band gap of the PN junction diode here. So, and very most important thing is, suppose if the forward current of the diode is small, then what will happen is, the intensity of the photons or the light energy which is being produced, that will also be very less. And suppose if the forward current is more, what will happen is, the intensity of light will be more and it will reach a maximum limit. So after this maximum limit, what will happen is, the intensity of light will become less. So the LED has a certain limit. So beyond that limit, it will not produce the same intensity of light. And next, we'll see the difference between an LED and a photodiode. So LED is a light emitting diode. A photodiode is a light detecting device. And LED operates in forward bias, photodiode in reverse bias. The emission of light is the recombination of electron hole pair. But whereas in photodiode, it is a generation of electron-hole pair. And examples of LED, that is the PN junction diode materials what we will use is gallium arsenide, gallium phosphide, and for our photodiode we use silicon and germanium. Even though silicon and germanium are the semiconducting materials, we will not use it for LED because silicon and germanium, they cannot be used in forward bias, and they will not allow light emission. The wavelength will be very small. So that's the reason we go to gallium arsenide and gallium phosphide. Sorry, we use gallium arsenide and gallium phosphide. What are the advantages of LED over the normal incandescent lamps? Is they are small in size and they'll be light in weight, and we get it in different colors. It has long life and it will operate in less voltage. So that's the reason earlier from earlier tube lights we have moved on to LED lights, and then it has less power. It consumes less power and it has that fast on and off switching capacity. So these are the advantages of LED. So here I have listed out few applications of LED in our day-to-day life. That is, you have LED TV, LED lamps that has been used in signals and that digital display, and even we use this LED lamps for room decorations also. So the next we are going to see about how a solar cell works and what. Now we'll see about the solar cell. The solar cell is a device which converts solar energy into electrical energy. So in a solar cell, again we will be using a PN junction semiconductor diode. So what happens here is, so the solar energy will be converted, the energy what we get from the sunlight will be converted into electrical energy. So we'll have a PN junction diode, and at the top we'll be having a metallized finger electrode. So that's the top surface which will be used as for collecting the electrons, and we'll have a back contact. We'll see the working of the solar cell here. So you have a PN junction diode, and you can see we do not give any forward bias or reverse bias. It is just connected to the load or the device. So the working of the solar cell consists of three processes. The first process is generation. So what happens in this generation is, so during this process, the electron hole pair will be generated, and so when it will be generated is, so when a light of energy which has an energy h nu greater than the energy band gap is falling upon the PN junction diode, an electron hole pair will be generated. Then the next process is separation. So as the name says, it is going to separate the electron hole pairs which are present in the depletion region here, and this separation will be due to the electric field in the depletion region here. And then the last part is the collection. So the third process is collection. So it is nothing but the front and back contact of the solar cell will be collecting the electrons and the holes here. So in the collection, what happens is the electrons will reach the end side and they will be collected by the front contact, and the holes will be reaching the P side, and these holes will be collected by the back contact. So what happens at this point is the P side will become positive and the N side will become negative, and this will give rise to a photo voltage here. And when you connect this to a load or an electronic device, what happens is current will be flowing through it here. So this is the working of a solar cell. Then we have certain criteria for the selection of material for the solar cell fabrication. So what are the criteria we'll see? So first one, the band gap. The band gap's range should be approximately equal to 1 to 1.8 electron volt, and the material should have high optical absorption, should have good electrical conductivity, and then the raw material should be easily available and it should be less cost also. What are the uses of the solar cell is? So solar cell will be used in it will be used to power electronic devices in satellites and space vehicles. And sometimes, and also it will be used as power supply for some calculators also. So as we had the VI characteristics of LED and photodiode, we have characteristic of the solar cell also. So this is, we can plot a graph for the voltage and the current here. So here what happens for a solar cell, the graph will be always plotted in the fourth quadrant. So why? Because the energy, the current which is being drawn by the load, it is not, the solar cell does not draw current, but it supplies the current same to the load. So it is not drawing the current, it is supplying the current to the load. So that's the reason we draw this graph in the fourth quadrant here.